Long context and usable context are not the same. Hi, I'm Mehrdad, and in this video, we'll look at a common problem. A model can accept a very long prompt and still miss important information inside it. We'll see why this happens, how to measure the amount of context the model can truly use, and when long context, retrieval, or memory is the better design. A model can accept millions of tokens and still give the wrong answer. Consider a long case file, where the facts are all present but spread across many sections. To answer correctly, the model must find each fact, keep it in the reasoning chain, and connect it to the others. The entire file may fit in the prompt, yet one missed fact can still break the answer. Adding unrelated text can make this harder because the useful evidence becomes less clear. This gives us two different questions. How much text can the model accept, and how much can it use reliably for this task? If this series is helpful, like and subscribe. Next, we'll define those two measurements and keep them separate. We need two length measurements, with a basic run check between them. Accepted length tells us how many tokens the API allows in one request. A completed run tells us only that the request finished without an error. It still does not show that the answer is correct. Usable length asks how much context the model can use while it still finds evidence, connects facts, and meets the quality target. That target changes with the task. A search may need one fact, a summary may need broad coverage, and a multi-hop question may need several connected facts. This is why accepted, completed, and useful must stay separate. With those measurements clear, we can now look at the cost of making the accepted window larger. Longer context costs more even before we check whether the answers remain good. With standard full attention, the amount of attention work grows roughly with the square of the sequence length. Faster kernels reduce the real runtime, but they do not make very long prompts free. During generation, the model also stores key and value vectors from earlier tokens in a key value cache. This cache grows with the sequence, so longer prompts use more memory, leave less room for batching, and often increase latency. Sparse or local attention can reduce some of this pressure by limiting which tokens interact with each other. The important point is that compute and memory costs arrive as soon as the window grows, while usable quality still has to be tested. Models usually train mostly on sequences within a limited length range. Positions inside that range follow ordering and distance patterns the model has seen many times. When a prompt goes far beyond the training range, those position signals may become unfamiliar. We call this position out of distribution. The model must now handle positions and distances that appeared less often or did not appear at all during training. Context extension methods try to make this transition less damaging, but accepting tokens beyond the training range does not prove that the model can use them well. We still need to test whether task quality holds there, and that test must use the right metric. One common metric can make a context extension look stronger than it really is. Perplexity measures how well the model predicts the next token. Retrieval asks a different question. Can the model find and use information located far back in the prompt? A model can show good perplexity while still missing distant facts. Context extension methods also take different approaches. Yarn and long rotary position methods rescale rotary position embeddings for longer ranges. Another method drops positional embeddings after pre-training. Hybrid designs, including interleaved rotary position embeddings, use them in some layers and leave them out of others. These are different design choices, not levels in one ranking. None of them guarantees useful long context, so test distant retrieval, aggregation, and multi-hop reasoning directly. Location can change the answer, even when the whole prompt fits inside the accepted window. Models often use information near the beginning and end better than information placed in the middle. This pattern is called lost in the middle, and it often appears as a U-shaped quality plot. Newer models may reduce the dip, but we should not assume that the center is safe. Moving every important fact to an edge may improve one test, yet it does not remove the model's sensitivity to position. A better evaluation repeats the same task with key facts near the start, middle, and end. A usable window should support the task across all three positions. A needle in a haystack test is a useful starting point. but it is often easier than a real application. The test hides one exact phrase in a long prompt, and the question may repeat many of the same words. In that case, the model mainly needs to find a close text match. Multi-hop reasoning is harder because the model must connect facts from different places, while aggregation combines many pieces into one answer. A model can pass the easy needle and still fail these tasks. Ruler measures the length where quality stays above a chosen target, and NoLiMa makes retrieval harder by changing the wording between the question and the hidden fact. Use several tests rather than trusting one score. Define usable length with the hardest behavior your application truly needs. Before choosing an architecture, describe the job with 4 practical questions. First, what will a long prompt cost in latency and money at the traffic you expect? Second, how often does the information change, and how harmful would an old answer be? Third, how large is the source collection? A small and stable collection may fit in one prompt, while a large or growing collection usually will not. Fourth, does the answer need one local fact, several connected facts, or a summary across many documents? These questions describe the real requirement. Cost, freshness, corpus size, and reasoning needs should guide the choice, not the largest context number shown on a model page. Now we can match those requirements to a system design. Use long context when the evidence is small, stable, and useful to keep together, such as one case file or one section of a code base. Use retrieval augmented generation, or RAG, when the collection is large, changes often, or includes document permissions. Retrieval selects a smaller set of relevant evidence before the model answers. Use summaries or external memory when the system must keep important state without replaying every earlier token. These choices are not exclusive, and many production systems combine them. Retrieval finds the evidence, long context supports reasoning across the selected set, and memory keeps useful state between turns. Remember 3 points from this lesson. Accepted length is not the same as usable length because a request can fit while the task still fails. Test the real behavior across the whole window, including difficult retrieval, connected reasoning, and evidence placed in the middle. Then choose long context, retrieval, or memory from the cost, freshness, collection size, and reasoning your application needs. I'm Mehrdad, and in Video 8 we'll look at multimodal inputs and how models combine text, images, and other data. Subscribe if this was helpful, and you can also find me on LinkedIn.